Hello, everyone. I just wanted to make a quick video to replace class today, Monday, November 28th. Sorry I couldn't be there today, but this will replace class today. So we are going to cover the homework 12 word problems. So um, you should have done all of homework 12 except for the 4 word problem topics before break. So today I'm going to go through with you how to complete the word problems for homework 12, and the homework for that will be due on Wednesday, which is November 30th at midnight. So without further ado, here we go. There's really just 3 formulas that you'll need to know to complete the word problems. The first one is a compound interest formula. This is probably something you've seen before, but it might have been a while, so I just want to refresh your memory. The compound interest formula is A equals P times the quantity 1 plus R over N, all to the N times T. So this is what the compound interest formula looks like. Let's go through what all of these things mean. So this A, this is the amount of money in the account at time T. So the compound interest formula basically tells you how much money is in a bank account that is compounded a certain number of times per year. So A is the amount that's in the account after it's been in the bank for T years. So that's what A is. It's the amount currently in the bank. P is the principal. It's an A-L is how you spell that. It's the principal, which basically means the starting amount. This is the amount that you originally put in the bank, the investment amount. That's how much you invested at the beginning. And this formula assumes that you don't add any money or you don't take any money out. P is the principal. You put that money in the bank and it sits there and is compounded. And A is the amount of money in the account at time T. A couple other things go into this. We've mentioned that T is the time in years. It's the amount of time that that money has been sitting in the bank, and we measure that time in years. It's always going to be in years. Part of the reason for that is because R is our annual interest rate. Annual means each year, and so R and T have to work together here. R is the annual interest rate, and so T is the time in years. Both of those have to be in years. And then N is the number of compounding periods per year. And so basically, compounding periods mean how often interest is calculated and added to the account. And this is going to happen a certain number of times each year. So common values of N are, so if you see something that says compounded annually, that has an N value of 1. It's compounded once per year. If you see something that is compounded semi-annually, that means there are 2 compounding periods per year. If something is compounded quarterly, that means there are 4 compounding periods per year. If something is compounded monthly, that means there are 12 compounding periods per year. And finally, if something is compounded daily, that means there are 365 compounding periods per year. So these are some common values of N. So all of that goes together to create our compound interest formula here. It's kind of big and complicated, but I promise it's going to be doable. So let's practice how to set all of this up. Okay, so James needs $2,158 for a project. He has $2,000 now invested at an annual interest rate of 3.4%, compounded quarterly. Assuming no deposits or withdrawals are made, how long will it take for him to have enough money for his project? Round to the nearest hundredth. Okay, so James needs a certain amount of money, and he wants to know if he puts $2,000 in the bank now with an annual interest rate of 3.4% compounded quarterly, how long will it take for there to be $2,158 in the bank? Okay, so let's start figuring out what all of this stuff is. So since he has $2,000 that he's investing now, that's our starting rate, that's our principal. So that means that P value is $2,000. The annual interest rate here of 3.4%, that's our value of R. Something that I should have mentioned up here is that R is our annual interest rate written as a decimal. I didn't include that before, but that's also part of this, is that our interest rate must be written as a decimal, not a percent. So when we write this annual interest rate of 3.4% for R, we're going to change that percent back to a decimal. And to write it as a decimal, you're going to move the decimal point 2 spaces to the left. And so that means our R value is going to be 0.034. That's our value of R. Because this thing is going to be compounded quarterly, that means our N value is 4. And he wants to know how long it's going to take to have $2,158 in the bank. That's the amount A that we want to be in the bank. We just don't know what the time T is. That's what we're going to be solving for. So let's plug all of these values into our formula up here. So my A value is $2,158. My value of P is $2,000. And then I'm going to have the quantity 1 plus R is 0.034 over 4, all to the 4 times T power. I'm just plugging in what I have. So my A equals P times the quantity 1 plus R over N, that quantity to the N times T. Plugged in everything that we had, and T is the only thing that we don't have here. And T is what we're looking for. How long will it take? That's a value of T. We have to solve for this. Okay, so now we have to figure out how to solve this equation for T. This is kind of a big, scary looking equation. And so the first thing that I would do is take this 1 plus 0.034 over 4 and put that in your calculator to get a decimal out. We don't often want to work with decimals, but here, because this is such a kind of big, bad equation, I think that's going to simplify our lives here and let us see this structure a little bit more. So if you take 1 plus 0.034 over 4 and put that in a calculator, you'll get 1.0085. Okay, this looks a little better to me already. I need to get to T. And this is an exponential equation here, right? I've got T, my variables, and an exponent. I need to solve this exponential equation. To solve an exponential equation, you need to get the exponential part by itself first. We need to isolate this, which means we need to get rid of that 2,000. The 2,000 is connected by multiplication here. So to undo that, I'm going to divide both sides by 2,000 here. And that's going to get rid of the 2,000 here, so I can get the exponential by itself. 2,158 divided by 2,000, you can put that in a calculator, and you get 1.079, and that's going to be equal to 1.085, oh, sorry, 2 zeros. If I can write that correctly, all to the 4t. Okay, this is an exponential equation. I have the exponential isolated. So now what we have to do is introduce a logarithm. Let's take the log of both sides. You can choose what base you would like to use. You can use really any base you want. I would advise you to use either log base 10 or log base e to make the calculator part easiest. So let's do log base 10. That's the one that I'll use here. So I'll do log base 10 of 1.079 equals log base 10 of 1.0085 to the 4t. Now that I've introduced a logarithm here, what that lets us do is take this power inside a logarithm and put it out front. So I'm going to have log of 1.079 equals 4t times the log of 1.0085. And now to get t by itself, I'm just going to divide both sides by 4 times the log of 1.0085 to get that t by itself. Because 4 times the log of 1.0085 is just a number. That's something we can put in our calculator. It's just a number. We can divide by it. Okay, when I do that, I have t left over here because everything else cancels. And I can take log of 1.079 divided by 4 times the log of 1.0085. When you're putting this in a calculator, make sure you put parentheses around that whole denominator so that your calculator doesn't get confused with order of operations. And when I put that in a calculator, I got 2.2458. Okay, so now let's make sure that we answer the question. How long will it take for him to have enough money? Round to the nearest hundredth. That means I'm going to round to 2 decimal places, and t equals 2.25 years because time is measured in years. And that answers our question here. All right, so that's the compound interest formula. I know it's kind of a big, scary equation, but kind of work with it piece by piece. Start to identify what each of the numbers that you're given represent, and then plug them in and solve for what you don't have. You'll always be solving for t here, so this is kind of what your process is going to be like. Make sure you divide off this p-value first to get the exponential by itself. Then just take the log of both sides and you will be off to the races. Okay, the next formula that we're going to see is exponential growth or decay formula. So basically this is exponential growth or decay that's not as specific as the compound interest formula. There's no compounding. It just means that something is growing or decreasing but with an exponential form, I guess. So the formula for exponential growth or decay looks like y equals a times b to the t power. This is your general formula for exponential growth or decay. Y is going to be either it can be an amount of money or it can be a population. These are the kind of most commonly used things for this kind of formula. It can be an amount of money, it can be an amount of items being produced, it could be a population, it could represent a lot of different things. But basically, y is going to be the amount or the population that you have at time t. T is the time in years. A is our initial, sorry, I can't spell initial. Spelling's not my forte. All right, A is the initial amount or the starting amount at time t equals 0. It's what you started with. And then b is the base of our exponential, and this is going to tell us whether we're dealing with growth or decay. If our base b is greater than 1, then we have exponential growth. Exponential growth. And if our b value is between 0 and 1, if it's a fraction, then we are dealing with exponential decay. So this is our basic exponential growth or decay formula. Y equals a times b to the t. Y is the amount or population that you have at time t. T is the time measured in years. A is our initial or starting amount when the time was equal to 0. And b is our base. We might also be asked for the rate of growth or decay, or the percentage growth or decay. That's going to be something called R. And that's going to be a rate of growth or decay. And to find this, it's really going to depend on whether we have growth or decay. And we're going to write that as a decimal. It really is, it's a percentage, and you might have to transfer it into a percentage, but R itself will be a decimal. So if you need to turn it into a percentage, then just make sure that you multiply by 100. That's how you kind of turn something into a percentage. Now, to find this rate of growth or decay, so if you have exponential growth, if your b value is greater than 1, then our rate of growth is going to be b minus 1. And if we have decay, if our b value is between 0 and 1, then our rate of decay is going to be r equals 1 minus b. It's basically always just how far from 1 your b value is. But whether b value is bigger than or smaller than 1 depends on how you find that. So this is how you find your rate of growth or decay. Okay, so let's practice with this. The way that we're going to be working with this formula are going to be problems that look like this. So suppose the future price P of t of a certain item is given by the following exponential function, where P of t is measured in dollars and t is the number of years from today. So P of t, this is the price. 2,500 is going to be our A value. That's our starting value. Our B value, our base is 1.049, and then it's all to the t power. Okay, so what is the initial price of the item? Well, our initial price is our starting price. That's our starting amount. And here, that's our A value. Our A value is 2,500. So the initial price of this thing is 2,500, and it's a price, so it's in dollars. So that's the initial price. Does the function represent growth or decay? Because our b value is 1.049 and that's greater than 1, we are dealing with exponential growth. Because our b value is going to tell us whether we're dealing with growth or decay. And then by what percent does the price change each year? By what percent does the price change? This means the rate of growth. That's what we're looking for. This is asking for that value R. So that R value tells us by what percentage we are growing or decaying every year. Because we have exponential growth, we're going to calculate our R value by doing B minus 1. So R equals our B value, which is 1.049 minus 1. That means our R value is 0.049. To write that as a percentage, we're going to multiply that by 100, and that's going to give us 4.9%. So that means each year the price of this thing is growing by 4.9%. Okay. The next one, a study is done on the number of bacteria cells in a petri dish. Suppose the population size P of t after t hours is given by the following exponential function. P of t equals 2000 times 0.85 to the t power. And you know what? I think before I told you that the time had to be in years here. It actually doesn't have to be in years on this one. Sorry about that. It's just the time. Sorry about that. The one that needs to be in years is um, the compounding formula that we just did. But this one, time doesn't actually have to be in years. So I apologize for that. I was wrong there. The time can be any units here. Apologies for that mistake. Okay. And so here our time, instead of being measured in years, it's actually measured in hours here. So that'll tell you what your time is measured in. Okay, so a study is done on the number of bacteria cells. P of t is our population size, and it's given by 2000 times 0.85 to the t power. So this is our A value, which is our starting value. That's how many bacteria there were at the very beginning. And then our base is 0.85. All right, so the initial population, we just kind of mentioned that. That's the number of bacteria we started with. That's 2000. Does the function represent growth or decay? To figure that out, we need to look at our B value. The base of our exponential is 0.85. That's less than 1, so we are looking at decay. And then by what percent does the population change each hour? That by what percent, that means we're looking for the rate of decay R. Okay, so to find R with a decay, our R value is going to be 1 minus B, and our B value is 0.85. So that means our R value is 0.15. We're going to multiply that by 100 to get a percentage, and that's going to be 15%. And that is our rate of decay. So that means the population is decreasing by 15% each hour. All right, and so that is how we use a general exponential growth or decay model. And then the very last formula that we'll be dealing with is continuous exponential growth or decay. Continuous means it's always growing. This can be used to measure populations, or it can also be used to measure money. The difference between this and the compound interest formula is that with compound interest, interest is calculated and added a certain number of times each year. With continuous growth, if it was measuring money and investments, continuous interest would be interest is calculated every moment that money is in the bank, and it's added every moment. So you would get interest for each second or each fraction of a second that it's sitting in the bank, rather than getting interest for every year that it's in the bank or every quarter that it's in the bank. So continuous exponential growth or decay means that things are constantly growing or decaying at a certain rate, but it's all the time. It's not a kind of annual thing. Um, so continuous exponential growth or decay, this formula looks like y equals y sub 0 times e to the r times t. And you know that you be using this formula. It has to say continuous growth or decay. This word continuous means that the base of your exponential is e. That's kind of what sets this one apart. Now, what all of these things are, this is going to feel very similar to what we've been doing. Our value of y here is going to be the amount or the population at time t. T, again, is going to be our time. And again, this one can be measured really in any units that you would like, because it's continuous, and the everything's going to be growing every second, every moment. Time can be any units it would like to be in this one as well. Y sub 0, this is our initial or starting amount. And again, starting amount means time equals 0. And then R is going to be our rate of growth or decay. To tell whether it's growth or decay, if our R value is greater than 0, if it's positive, we're working with growth. And if our R value is negative, we're dealing with decay. The reason for this being positive or negative versus greater than or less than 1 is because this time the exponent tells us whether we're dealing with growth or decay. And in the previous one, it was the base of the exponential was telling us whether it was growth or decay. So when we have an e as our base, if our exponent is positive, we're going to be growing. If our exponent is negative, we're going to be decreasing or decaying. And again, that's because negative exponents give us fractions. It's actually going to reduce the amount that we have. Okay, so let's do an example of this. An initial population of 730 fish is introduced into a lake. The fish population grows according to a continuous exponential growth model. There are 949 fish in the lake after 13 years. Okay, let t be the time in years since the initial population was introduced, and let y be the number of fish at time t. Write a formula relating y to t. So we need to come up with a formula for this. Because it says continuous exponential growth, this word continuous means that the base of our exponential is going to be e. We're looking at this formula right here, continuous exponential growth. So we just need to figure out, we're going to be using y equals y sub 0 times e to the r times t. We just have to figure out what all of our values are. So let's see what we've got here. We know that an initial population of 730 fish is introduced. The initial population of 730, because that's our initial or starting value, that means our y sub 0 is going to be 730. And then the only other information that we're given here is that there are 949 fish in the lake after 13 years. So that's telling us that y, which is the amount or the population, is 949 when our t value is 13 years. Okay, so we know y sub 0 is 730, and then y is 949 when t equals 13. So our growth, exponential growth or decay model is going to be y equals 730 times e to the r times t. To have a formula, we need to figure out what r is. We can leave y and t as variables, but we need to figure out what this r value is. I don't know what the value of r is. And that's what we're going to use this extra piece of information. We're going to use this to figure out what r is. So we know that y is 949 when our t value is 13. So we're going to plug 949 into y and 13 into t. And then we just have to solve for r. Okay, so how do we solve for r? Well, this is an exponential equation, so I need to isolate my exponential just like we did before. We need to get the exponential by itself. To do that, I need to get rid of that 730. It's connected by multiplication, so I'm going to divide both sides by 730 here. 949 divided by 730. We can put that in a calculator and you would get 1.3. The 730s go away and I have e to the r times 13. I'm going to write that as 13r because my brain likes that better. Okay, so now we have the exponential by itself. From here, to solve this out, we need to introduce a logarithm. You can choose any base you want. I'm going to choose log base e, or the natural log, just because it's going to make life a little easier to solve. So if I take the ln of both sides here, this is the log, the natural log is log base e. Since I have a base of the logarithm as e and the base of the exponential is e, the base cancels the base, and I have 13r left over here. So the ln of 1.3 equals 13r. Now to get r by itself, I just have to divide both sides by 13. And the ln of 1.3 divided by 13, you can put that into a calculator, and I got 0.02018, and that's our value of r. So now to get our formula, because the answer here is we want a formula relating y to t. That means we can leave y and t in our formula. We need everything else. So I'm going to plug in my y sub 0 of 730. And I'm going to plug in my r value. I'm going to round this to 2 decimal places. And that is my formula. Y equals 730 times e to the 0.02t. All right, the very last thing, how many fish are there 14 years after the initial population is introduced? Well, that means I'm looking for y, how many fish, that's looking for the population, at time 14. So that means t equals 14, and I want to know what y is. So to figure that out, I'm going to plug in what I have. E to the 0.02 times t is 14. And I can just plug this in a calculator. 730 times e to the 0.02 times 14. Again, when you put this in a calculator, make sure you put parentheses around here so that your calculator knows that whole multiplication is in the exponent. And when you do this, I got 965.88. And they wanted you to round to the nearest whole number. So that means we're going to have 966 fish after 14 years. And that's the answer to this. All right, so those are the word problems that you'll be seeing. Um, the only other kind of word problem we actually did before break, where it was identifying an initial amount and then just plugging a value in. So I think you'll be um, pretty solid on those two. Um, I will be answering email all day, so if you have any questions, please let me know. The rest of homework 12 is due Wednesday at midnight. If you have any questions about the homework, you can ask me at the beginning of class on Wednesday as well. I hope you had a great Thanksgiving break, and I will see you on Wednesday.